So in this video we're going to look at chemical equilibrium, and we're going to introduce the idea of what it is, and we're going to briefly touch on Le Chatelier's principle. So our learning intentions are to discuss reversible reactions and link them to dynamic equilibrium, to explore equilibrium law, and to define Le Chatelier's principle and its consequences. So to begin, we need to kind of understand what the word equilibrium means. So if you look up equilibrium in the dictionary, you'll actually find that it's explained using the words state of balance. So an example of this would be if you got a meter stick and its center of gravity remains stationary when we have something called static equilibrium. So if you hang a meter stick from a string, and if we were to put weights on either side of our meter stick, so here's our meter stick and it's hanging from a piece of string. Once I put the same weight on each side and an equal distance from where it's hanging. So if it's hanging at 50, if I hang a weight here at 30 and I hang a weight here at 70, and if they are both the same weight, so let's just say 1 gram and 1 gram, the meter stick will be balanced. And at this point you would say that the meter stick has static equilibrium, so it is not moving. So with static equilibrium, we mean that the system or the object is not moving. Next, we're going to move on to dynamic equilibrium. And an easy example for this is an athlete running on a treadmill. So as the athlete is running, they're not changing position. They are running forward at the same speed. The belt is moving in the opposite direction on the treadmill. So as the runner runs, the belt moves in the opposite direction at the same speed. And this is dynamic equilibrium. So dynamic equilibrium basically implies that there is movement. Now, on our Leaving Cert course, we are going to be looking at dynamic equilibrium. So we are going to be looking at reactions that involve movement of particles and molecules. So, with chemical equilibrium, we can look at many chemical equations, and many chemical equations do not go to completion. So, for example, if we take the formation of ammonia by reacting hydrogen and nitrogen, the reaction does not go completely from left to right, because the ammonia can decompose to form nitrogen and hydrogen. So if we look down here at the equation we have for the formation of ammonia, we see that the nitrogen and the hydrogen can react together to form 2 ammonia molecules. However, at the same time this is happening, some of the ammonia molecules may break down to form your nitrogen and your hydrogen molecules again. So this was discovered by a scientist called Fritz Haber, and we call this the Haber process, which I will go through in greater detail in another video. But the main thing that we can see here is that the reaction can go in both ways. So we can have the nitrogen and hydrogen forming ammonia, but the ammonia can also decompose to form the nitrogen and the hydrogen. So at that point, we could say that there is both a forward and backward reaction. So that would mean that we could call this a reversible reaction. So that's what I said here at the top. It's a reversible reaction. So our definition for a reversible reaction is a reaction in which once the products are formed, they react to form the initial reactants. So basically you have a forward and a backward reaction. So your reactants will go to form your products, but the products can also go to form the reactants. And equilibrium is represented by this yellow arrow that I have drawn in here. These are called equilibrium arrows. So it's basically a left arrow with half a head and a right arrow with half a head. In a reversible reaction, we say that a state of equilibrium is reached when the forward reaction, i.e. the reactants going to the products, and the backward reaction, products going to reactants are happening at the same speed, which would mean that there is no change overall in the amount of reactants and products that are present. So that is actually our definition for chemical equilibrium. So it's a state of dynamic balance in a reversible reaction where the rate of the forward reaction is the same as the rate of the backward reaction. So if we were to look at that for ammonia, where we have N2 plus 3H2 goes to 2NH3, we would know there that the reaction is at equilibrium when the rate of the forward reactions, the production of ammonia, is the same as the rate of the backward reaction, which is the production of the nitrogen and the hydrogen. That means that the nitrogen and hydrogen are forming ammonia at the same speed as which the ammonia is breaking down and forming the nitrogen and hydrogen. So if we think about it, it would make sense to say that at the start of an equilibrium reaction, the rate of the forward reaction is much faster than the reverse reaction. And after the two speeds become the same, we can then say that our reaction is at equilibrium. So I've just drawn out a kind of graph diagram here to help you understand what we mean by equilibrium. So as we can see, the red line represents the concentration of nitrogen, the yellow line represents the concentration of hydrogen, and the green line represents the concentration of ammonia. So if you look at the very start, when time is 0, the concentration of nitrogen and hydrogen, they have these fixed values here. Now the reason the hydrogen is higher is got to do with the number of moles of the gas that's placed in the container. And you'll see that the initial concentration of your ammonia is 0, because that means at the start of the reaction you have your reactants ready to go and none of your product has formed. But as the reaction proceeds, you can see here that the concentration of the hydrogen and the concentration of the nitrogen begin to slowly fall, and that the concentration of the ammonia increases. So here what we see is once we get to this point kind of here in the middle, we can see that the concentrations start to level off and become stationary. So all the concentration of all three substances in the container that this reaction is happening is becoming constant. And once we reach this stage here, we can say that the situation in the container is described as dynamic equilibrium, because the nitrogen and the hydrogen are consistently reacting to produce ammonia, but the ammonia is then consequently decomposing to form nitrogen and hydrogen. So based off the last graph, we have a dynamic state where the reactants are continually forming products and the products are continuously forming reactants. And when a reversible reaction has reached equilibrium, we actually say that it is a dynamic equilibrium. So a dynamic equilibrium is one where the rate of the forward reaction is equal to the rate of the reverse reaction. And we've shown that in our diagram. So next we're going to look at Le Chatelier's principle, and Le Chatelier's principle was put forward by a scientist called Chatelier in around 1880s, and he put forward a rule that allowed chemists to basically look at the direction of the equilibrium reaction, so whether there was more forward reaction happening or more backward reaction. And he said that if a system at equilibrium is subjected to a stress, that the system will alter to oppose the effect of the stress. So basically when he says stress, he means a change in the condition of the system for a system that contains gases. So if we change the conditions of the reaction that has reached a state of equilibrium, the equilibrium will basically be shifted in such a direction that the effect of that change will be minimized. So we will basically be trying to oppose the stress. So Le Chatelier's principle predicts that all gaseous reactions, an increase in the pressure will favor the reaction that brings about a reduction in the volume. Now, it's important to remember that a change in pressure will only affect an equilibrium reaction with unequal numbers of gaseous products and reactants. And the equilibrium will always shift to the side with the smaller number of molecules. A catalyst does not affect the position of the equilibrium in a reaction. It only speeds up the rate at which equilibrium is reached. So our catalyst won't affect where the equilibrium will be. It will only speed up the rate at which the equilibrium is reached. So let's look at Le Chatelier's principle with respect to this reaction that we have here. So we have COCl42-, that's a blue colour, and that's reacting with water. And our equilibrium reaction says that that will form COH2O6, 2+, and 4Cl- ions. Now, if this was just a normal reaction, we would be able to clearly indicate that our colour change during the experiment would be from blue to yellow because the reactants are blue and the products are yellow. However, this is an equilibrium reaction. So in an equilibrium reaction, the forward reaction and the reverse reaction are happening at the same time and at the same rate. So you would have a mixture of those colours present. So the first thing that we are going to know is we're going to know that the delta H is positive for the reverse reaction, so when we're forming the reactants, and delta H is negative for the forward reaction when we are forming our products. Now, when delta H is negative, we say that the reaction is endothermic or cooling, so our reverse reaction is a cooling reaction. And when delta H is negative, we say that it's an exothermic or heating reaction. So the forward reaction is a heating reaction. And you'll have met delta H already and the words exothermic and endothermic in our fuels and heats of reactions video. So what happens if I add heat to the reaction? So if I heat it up, the first thing is heating is a stress. So we know that according to Le Chatelier's principle that the reaction will change itself in order to counteract this stress. So if you heat something up, it's automatically going to want to cool down. So with Le Chatelier's principle, the opposing reaction occurs, so we'll want the reaction to cool down, and that is the reverse reaction. So that means that our products will start to break down to reform our reactants. So that would mean that we would have a colour change from yellow to blue because our reactant side is now being favoured. The reverse reaction is being favoured where the products breaks down into the reactants. So that's it for this video. Have a read over the learning intentions to make sure you understand everything we've gone through.